Next speaker has 20 years of technology experience, has 5 software companies under his belt that have been acquired, has published numerous articles on databases and big data, and has spoke at hundreds and hundreds of tech events. Please welcome the CTO and CEO of CodeFutures, Cory Isaacson.
So thank you all. Now I just have to work out how I can speak in the mic and not kill myself getting to the computer to change the slides. Anyway, so I have spoken at a lot of events, written some books and things like that. I'll give you a little bit of background on me. But I can tell you this is the first time I've had to do like a nightclub act. So anyway, so just a little background there. I told you a little bit about me, but I am the CEO and CTO of CodeFutures. We're a small company, so I'm more the CTO than the CEO. That's how it really works in practice. I actually wrote a book in 2007 called Software Pipelines, and you can find it on Amazon if you're curious about it, but it was a technique that we developed at my last company, which was Rogue-Wave software. Anybody know Rogue-Wave? I know one person here does. C++ tools, .A++, and so some people. So I ran Rogue-Wave for about 4 years before starting CodeFutures. And the reason I started CodeFutures, which was literally the next day, is because we were working with all kinds of Wall Street companies here in New York and financial institutions and different companies, but mostly here in New York. And what we found was that we were trying to get applications to scale, and we had different frameworks to do that. But every time we did it, guess what the biggest bottleneck was? This is not a trivia question. You should know the answer.
Money.
The database. So the database was always the barrier, getting applications to scale. So when we sold Rogue-Wave, I said, wow, wouldn't it be a cool idea to start a company that did database scalability? So I took a few people with me when I left Rogue-Wave, and we started CodeFutures literally the next day and had a lot of fun since. So I'm also working on a new book which has some significance. I'll show you in a minute. But it's a new book on big data scalability. It's an ebook that's going to be out in, I don't know, maybe a month or two, something like that. But I have some more prizes that we can do for questions during the presentation. If you ask good questions, I'll give you one of them, but I'll show you what that is in just a minute. So, but basically, you know, the thing I want to say is that we have worked with, we were one of the early database or data sharding or scalability companies in the whole field. We started in 2007, and nobody even wanted to talk about scalable technology for maybe almost a whole year, actually. And then it was around 2009, some other companies joined in 2010, and all of a sudden, I think there are 300 companies in this space. I personally, I don't track it all, but I personally have seen something like $1 billion in venture capital go into this space. None of that was happening when we started, I can tell you that. But so we gained a tremendous amount of experience in this whole field. And we used it to build our dbShards technology. I'm not going to really be talking about that much tonight at all, but the point is we built a good product, we got a customer base, that was all fine. But we really wanted to go further. We really wanted to make this whole field easier. So I'm just curious, by show of hands, did any of you run into maybe a database performance problem in your career? That's good, because if you said no, then you're like in the wrong place. So, but I just want to ask a more serious question, which is, you know, when you have to tackle these challenges with today's tools, the databases are getting much more capable. There's a lot more choices, but I have to say that I have respect for all of you because this is like really hard, right? Have you ever noticed it's really hard to fit your application requirements to the databases, figure out which ones to use, how to structure it, what's the best way to take advantage of it, how to scale it, manage it, especially if you have a big data problem. It's really, really a challenge. And so one of the things I really love about this field is that I really think I get to work with like the smartest people on the planet. You know, they say it's not rocket science, but it's pretty close to actually get all this to work. So it's really quite something. So really, I took a lot of that experience, put it into the book that I'm working on, but also we're working on a new product that you'll hear just a tiny bit about tonight at the very end. But mostly I want to talk to you about kind of our philosophy and what we've learned over the years of doing this. Because I think we've had easily as much experience, if not more, than any other company I know of in this field. And we literally have looked at hundreds and hundreds of database and scalability problems over the last 6 or so years. And anyway, I hope to impart some of that tonight, and I hope it's also useful. So my whole purpose is that you walk away with something you can actually use and take away and actually make something better, like tomorrow or next week. So what am I going to talk to you about? Well, one thing is I'm going to talk to you about scaling big data and the fundamentals of that. So I'm just going to do, that'll probably be about half the presentation. I can take questions on that. This isn't, I just want to be clear, this is not Hadoop MapReduce, talk. There's lots and lots of people who can cover that type of thing. And that's, I think, I've seen that done a lot of times. What I'm talking about more is taking normal business applications and things like that, and how do you really scale them, and what does it take, and what are the real principles underlying it. It doesn't really matter if you're using relational or NoSQL or new SQL or any of these types of technologies. There's a lot of commonality, and that's what I'm going to be talking about. A lot of the examples are SQL because, well, anyway, I've been in the field too long, and that's what I know. But I do have people on our team that know lots of other things as well. So, anyway, the second thing though is, we had kind of an interesting, last year. We basically have been growing the company a lot, and we really wanted to expand our horizons on what we were doing. And because of that, we started looking at the whole problem of how all this technology works. And like I said, it's really, really hard. And any of you think there's like room for improvement to make things easier to work with in this area with big data? Maybe just a little? So anyway, we got to talking about this with my team. And anyway, I have some really great people that I work with. One guy's name is Andy Grove. He's my partner in the company. He's the most famous chief architect in any database company. But it's not that Andy Grove. But anyway, he's worked with me for a long time. But anyway, I work with Andy Grove. I work with another guy named Jan Kotek. He's from Greece. Jan Kotek is the developer on an open source project called MapDB. And we're very happy to sponsor MapDB now, and Jan's been working on our team for about 6 months now, something like that. Anyway, and then I have a few other very, very bright architects, as well. And so we got to talking, and we said, can we really do a better job, and can we look at the problem a different way? And it's kind of interesting. So we actually really do believe that all of us have been looking at databases from a certain point of view, and we actually think it's maybe not the best point of view. And so you might not agree with what I say, but I'm going to tell you how we've kind of arrived at that conclusion, and then toward the end you can see what it looks like. And so what that will lead to is essentially an agile view of big data. And you saw the t-shirt, so you kind of know the punchline already. But your process is agile. You can develop software in a very agile way, but your database is anything but agile, right? And databases are really, if you're managing, terabytes of data, it's not going to be like you can just change it like that. And it's a problem because it really gets in the way of everything that we want to do. Lots of issues. Okay, so what I'm going to do now is just cover the scaling big data fundamentals first, and then we'll get into the rest. So, and if you have questions, you can ask me, and so I'll tell you about the prizes you can win if you ask good questions. If you ask questions that are too threatening, I don't know what to do. So, what is big data? That's the first thing, right? What is it really? And there's lots and lots of definitions out there. Go look at Wikipedia or whatever, right? What I know about big data is when you have a database problem, and especially if it's not going to fit on a single monolithic database server, it's a big data problem. It doesn't really matter if it's a 50 gigabyte database or a 50 terabyte database. It really translates into a big data problem. And if you're the one who has to support it, right, and your users are upset with you and things are going slow and it's crashing and you're working all weekend and all night to try and fix it, believe me, it's really a big data problem. And so that's really what we're talking about from a practical standpoint, right? But the key definition that I think is most important about what makes it really big data is as soon as you have to go to more than one server and partition your data in some way or another. And it doesn't matter really what database or technology you're doing. You could be working with MySQL, you could be working with Oracle, you could be working with MongoDB. They all do that. Right? They all have some capability to do that. So the basic idea of big data is when your database starts to break. That's a big data problem, and that's when you hit it. So this leads me into what the prizes are for the really cool questions. If you ask them while I'm talking, is that these diagrams, a lot of them are from the book that I'm working on. And so these are hand-drawn, original whiteboard diagrams that I drew myself. And so What the prize is I actually made hand-signed prints. Anyway, so I have 5 numbered prints that we brought. So what I'll also do, though, if any of you are interested, whoever gets a print, if you send us an email or give me a card or whatever, we'll send you a print. I can do 25 of them and a free copy of the book if you want. So that's an interesting to do that. So anyways, you have to ask, like I said, cool questions, and they have to be questions hopefully I can answer. But they're more than good questions. So we talked about databases are challenging, right? And so what makes them challenging is that they're basically broke. That's the problem with databases. I know 2 things from my career. And I've been developing database applications for a long time, even before I was doing database technology. And what I know is that a database always gets 2 things happen. It gets bigger and it gets more complicated. That's the only 2 things that are missing or totally consistent. The only time it gets simpler or smaller usually is if you threw it out and you started all over again. And that happens, sometimes every 5 or 8 years. People just get so sick of it that they actually go and do that. But the key is, as the database gets bigger, right, and this drive toward big data, how do we actually get meaning out of this data? Because it's no good if we can't actually get value easily for our organizations. We can't tell what it means or extract value when it really is kind of purposeless, right? And so, in a lot of places I have seen this where people have humongous, let's say Cassandra databases or other things, and they're not doing very much with that data actually other than capturing it. For a long time, Twitter is a good example. They were capturing, trillions of tweets literally, and then they were like, what are we going to do with all these 160 character messages? So, and it really was, really important to their content. So what's driving all this data is also just important. We've seen a huge expansion and explosion in data. I call this the big data explosion. You've seen it over the last, let's say, 10 years. Started with search engines, then we had social networks that were growing really fast. We have mobile devices everywhere now. We have system data that's been around for a long time. And now people are talking about the Internet of Things, IoT. And so when you look at the Internet of Things, basically what are we walking into is everything is going to have a CPU and a network connection. Pretty much everything. You're going to be able to wear, health monitors. You're going to have your car is going to start to communicate things, and just off your toaster, who knows what, right? It's almost like what. You remember when James Gosling was talking about Java originally in the early days, and they had this idea that Java was going to run in every appliance and be a network connected up. Anyway, that idea is not going to happen with Java, I can tell you that. But the idea is going to happen, for sure. And when it does, it's not that far away, we're talking about 100 times explosion. And now every business is going to have something to do with big data, even things that you would think never would have gotten involved in this. So it's really important, and I think incredibly valuable for you guys to know everything you can about this field, because it's going to be one of the biggest things in the whole world. It is now, but it's going to be much bigger, much bigger. So let's just talk about what it takes to scale an application architecture. So let's say you've got something that's successful. Any of you ever written in a company that really started to grow their data 10, 20 times, 100 times? You've been through that. It's very exciting, isn't it? It was a lot of late nights for me. You definitely have to work hard. So what does it really take to accomplish that, and what does it take to really handle it? So in a typical application architecture today, we have usually 3 tiers. There's usually some sort of, if it's an online application, we have a load balancer, we have the application server tier, and then we have a database tier. Those 3 tiers are pretty standard. There might be different variations. You could be doing analytics and other things that might not look exactly like this. So when you want to scale, you have to know how to scale each of these components. Well, scaling the application, in the load balancer is like a piece of cake, right? Because you can have more than one load balancer, and they're stateless. They don't keep track of anything. Every connection comes in, and it has some logic, round robin, whatever. They just use simple methods of distributing the calls. And then if one of them fails or anything like that, no problem. If it's not enough bandwidth, then just add a couple more and you're done. Right? It doesn't even take many of them. You can handle a huge amount of volume. So that's really easy. So when you're talking about, you're talking about scaling your application servers, it's almost the same thing. Sometimes application servers have some state. You might have cookies you're keeping track of that guide you to a session state or something like that. But otherwise, they don't really have any state in them. You can scale them out. You can shrink them. You can make it really elastic. It's just a piece of cake to do any of that stuff. And if one fails, who cares? Another one will just take over the next request. We don't really care about that. So where's the problem? Right? The problem is scaling the database tier. And so scaling the database tier is really hard. It's anything but easy. There's just no easy automatic way to do it. And even with all the advancement we've seen and all the tools, I don't know of one today that's actually a full piece of cake, no problem to manage product. Even our own products, I have to say, we did a pretty good job, but it still wasn't totally easy. But why? Why is this so important? Because one is, databases are stateful. After all, that's what they do, is they save information. So you have to have them. And so you can't just do away with that and say, oh, we don't really care if it goes away because it's got data and you need it. Right? The second is there are large integrated data sets. The more successful you are, the bigger those data sets are. If you get into managing terabytes or petabytes, let me tell you, it's really big. And if you have to do anything like that, it's like moving a freight train on your back. It's really hard to carry for us. They're very I/O dependent, and essentially, if the database goes down, you're really in trouble, right? Anybody ever lived through an actual database outage in a critical 24/7 application? It's not. What's that?
Hurricane Sandy.
Yeah, there you go, with Hurricane Sandy. So it's not the most, like you probably wish you didn't come to work that day. You at least had a good excuse. You had a good excuse. But a lot of times I can tell you it happens when the excuse is not that good. So anyway, but it's really, really difficult when the database goes down. So it's not only you have to scale something that's very difficult to scale, you have to make it reliable too. And those are all critical. So the database is what I call the last mile of database, of true application scalability. And one thing I'll talk about at the end, just briefly, is how we can make that whole process more agile. We're really doing some kind of very interesting work in researching that, and that's what I'll talk about as far as our new direction and philosophy. But so basically, there's a few pieces of advice that I've developed over the years. One is, if you have to scale your application and you're running into performance problems, the first thing is try and optimize what you have before you scale it out. That's the first thing you should do, is not scale it, because why? Scaling your database is a big deal. It's not going to happen overnight. If you think that it's something you're going to implement between now and next weekend or something like that, that's way underestimating how it's going to take, right? But at the same time, what you should be doing is, if you do have a growing data set, you should basically start planning now. And why? Because I can tell you more times than not, we get a call that somebody's totally panicked, their application is exploding, the database is crashing all over the place, and they call us way too late. Want it fixed in a couple hours, and it's not a couple hours. So it's really important to develop a strategy now. So I want to ask, how many of you have to actually manage more than one kind of database engine for work with it in your application infrastructure? Okay, cool. So I'm working with a company now, and we're giving them some advice, and I was just fascinated. They have one application. It's a big application. It's a lot of data that they're processing, but they have 12 different database engines in this application. 12. I've never heard of 12. I've heard of 2, 3, 4. Anyway, it's amazing, right? But it's so complicated. They have hundreds of people in their team, in their infrastructure team, but it's enormously complicated for the application developers to keep up with all this stuff, and the system administrators. So I don't recommend 12. But one thing that's happening, though, that you really have to say is true, is that the database engines are changing fast. They're changing really, really fast. And it seems like each engine is really good at a certain kind of job. Now, every vendor, including us, will tell you their database engine is the best for everything, right? So I can tell you that's not true, even when we say it. So the point is that each database is actually good at a certain kind of job. And what you want to do is use the database that's the best for what you want for that particular thing. So for instance, maybe you have to have some things in memory, maybe you have to have some things on disk because you need persistence, maybe you need transactionality over here, but not over here. There's all kinds of different characteristics. And it's not that hard to actually learn about these engines and pick the right one, and I really recommend doing that. That's a critical thing. So company that we've done a lot of work with called BigDoor. And you guys probably don't know who they are as a company, but has anybody ever gone to Starbucks.com or NFL.com, any of those websites? You know how you can earn points there? So the points are all managed by BigDoor. They're the biggest company in the what they call website gamification. So that's what they do. And so it's really a loyalty program. I call it a frequent flyer program for web users. That's really what it is. And the reason they do this, I didn't even understand what the advantage was, but the reason is if you go to NFL.com, there are certain pages that have ads on them. You probably noticed that, right? But they get paid a lot more for some kinds of ads than others. For instance, I think if you watch a video, that's worth a lot more points than the others. So the whole idea of these point systems is to actually help generate more revenue for that site because you're hopefully seeing an ad, which you're probably ignoring anyway, but they get paid more. So, but BigDoor is very interesting though because we started with them with a single monolithic database. That's what we started with. And today they're running on 32 server infrastructure of a scaled out database for one instance, which is MySQL, and that's their core transactional engine because they need transactional because why? They're keeping track of points and those points are worth many at some point. And so it's not like they can just guess at how many points you have. You have to be accurate. But then they had some other features like leaderboards and things like that that they were trying to do in MySQL that were just horrible. And so what they did was they were able to integrate pretty seamlessly Redis, which is an in-memory database. Anybody use Redis? Okay, cool. So it's a really nice product, right? It does a lot of things and it's easy to learn and work with, right? But it's kind of low level. But anyway, they were able to make their leaderboards inside Redis, and they made them incredibly powerful. And now the leaderboards are real time, whereas before they were running the leaderboards as a batch process like 3 times a day. So it means you could tell where you were on the leaderboard like 5 hours ago. It wasn't terrific. It wasn't terrific that way. But I bring them up because they had an infrastructure that really had to scale, and they had some relatively simple setup in the beginning, but it was really broken. It was really not going to make it. And one of the key things we usually see when somebody has to start to scale is if you have a single monolithic database, what we see is that there's a joke from the mainframe days, some of you may remember this, but it's that all CPUs wait at exactly the same speed. It doesn't matter how fast the CPU is, right? If it's waiting for disk, it's not going anywhere. So this is an actual CPU graph from a customer application on their database server. And what you can see is, this was running in the cloud, by the way. I won't tell you which cloud, but the biggest cloud, anyway. But you can see at the bottom, there's a little teeny strip of blue. That's the actual productive user CPU. All of that red is basically the CPU just waiting for I/O. That's what the whole thing is. And that's the most common thing that you'll see. So when your database is going to start to show signs of wear and getting tired, you'll start to see this kind of graph. You should grab it way before this happens. But this is what you want to look for. It's a very good indicator. Now, we talked about databases just get bigger. When they get bigger, what happens? They get slower, right? They don't get slower in a nice, pretty picture, right? Nice linear curve that you can say, okay, in 7 months and 3 days, I know I'm going to run out of horsepower, right? It doesn't work like that. What happens is, it happens in a hockey stick like this, in an exponential curve. And when it happens in a hurry. And it can happen for lots of reasons. We're going to cover some of the common ones. But the biggest thing we know is this is an actual, since I drew it, it's a very approximate graph, but I can tell you I know the statistics. But it is, we did some data load tests with a complex table. We had a customer that had a very complex table. It was a 40 gigabyte table, and it had 12 indexes on it. So it was really, really difficult. And they were having a lot of trouble just managing that in MySQL. So that's where we started. This was done years ago, this test. But it's still pretty applicable. And what happened was that because they had so many indexes and it was so complicated, we could load about a gigabyte in a minute. We could load about 3.5 gigabytes in 12 minutes. That all seemed fine. If we tried to load all 39 gigabytes, they went for 10 days and never finished. And this was on good machines with fast I/O and fast processors. Like 8-core machines with plenty of memory and everything else, right? So we got really curious about what really caused this. And what we found was, as the database gets bigger, the indexes get bigger, especially. And especially if you're doing writing, you'll see how this works. But basically, the indexes get much, much slower. And if you have lots of them like that, it's almost impossible to keep up with it. So it's really, again, a real cause where you're going to make a database just run out of gas because you have too complicated of a setup. So there are what I call the enemies, the common enemies of database performance. So one of them is something called a table scan. And I don't care what kind of database you're using, they will all do a table scan at some point. Every single one of them will do that. So what's a table scan? Table scan is basically you ask for a query, it has no index or something like that, or whatever. There's a lot of different causes, but what does it do? Who knows the answer?
Reads the disk.
Top to bottom. That's right. It's a disk read, right? It's not very fast either, is it? Right. So who wants a... Somebody should get a poster for asking the question or answer. There you go.
Clean it up.
By the way, Danny Sears is here working with me, so he has the rest of them. So you have to fight with him to get right after this. All right, so that's one. But there's kind of another common cause, right? So how many of you are DBAs? Nobody here. All the time. Okay, good. So have you ever seen what happens when one developer does one bad query? And one query, that's all it takes, right? It only takes one query, right? So you can have a gazillion fast queries that are all performing sub-second and everything's fine. And then one person makes one mistake, something wasn't tested or whatever, planned out right, or he didn't understand how it worked. You know, that one slow query will kill the response time. So at a couple of companies ago where I worked, it was a big public company, and they had this consulting group. And anyway, a friend of mine was running that. He brought me into the company to work there. And anyway, they called me up on a weekend, and they said, you know, we have this problem with this application, and we can't figure out what it is. And anyway, I listened to him, and I said, all right, I'll come over. So I came over on a Saturday, and I looked at what was going on, and didn't really look at anything. And I said, you know, you're missing an index somewhere. You got a table scan. You got one bad query in this whole thing. Because it was working fine, you know, on Wednesday, and then on Thursday it crashed, and they've been working, you know, 24/7 and trying to figure it out. And so anyway, so you know, it took them another day and a half or 2 days to find it and fix it. But it was just one query. It was just one query. And anyway, the developer and project manager who worked on this project, he goes, how did you know that? Anyway, because I made that mistake a lot of times myself.
So we have PeopleSoft and we have Oracle database behind it.
Yes.
And we have tables with 40 columns. We have 2 million rows in ES job table.
Yeah.
And we don't have any index, but we don't have any issues.
Well, that's okay though. If it's enough to fit in memory, or it depends what you're doing.
I don't know, it's a PeopleSoft application, like it's a
So I don't know how they do it. You know, I'd have to look at the structure. But it has to be big enough. I'll give you another example of when this is a problem. I think you get a poster though. That's good. So we'll have to go investigate PeopleSoft now. We'll have to profile and figure out why that's the case.
I came to another conclusion from ETL perspective. See, if you are loading like 20 GB of data, you have to drop all indexes, load it,
yes,
and then recreate index.
That's
then
right.
it helps. But if you are doing only 3 GB, then you should not do it this way.
That's right. There's going to be a certain limit, and it's going to be based on how much memory you have. Why? Because if the database can build the indexes in memory first, it's going to go 100 times faster.
Right. So I like different.
That's good. So you found the limit. That's good for what Oracle can do. But many years ago, I had a consulting company that was dealing with, at that time, leading database technology, which was Sybase. And we were one of the biggest, I know it isn't today, but then it was. Sybase was a really hot company, and we were the biggest Sybase independent consulting company in Southern California. So we helped Sybase crack all the entertainment companies. So we got into Disney and all kinds of fun places, fun applications. Well, one of the applications we actually built was for Fox Television. And I don't know how many of you will remember this, but there was only 3 television networks in the world, in the country, up until then. Fox was the 4th network. And they didn't have as much budget as ABC, CBS, and NBC, and so they wanted to build this system. And they said, we want to build the first integrated broadcasting system. That means controlling all the sales, all the scheduling, billing, the satellites, everything. So anyway, so we got that contract. It was a pretty cool deal actually to get. So it took us 2 years to build it, right? We got it, implemented. There were about 100 users, something like that, corporate users that were using it around the country. And everything was going fine for 2 months. It was amazing. For 2 months it was all fine, right? Then all of a sudden, this happened. And one day we came in and it was like everybody was screaming. They go, it's taking 20 seconds to bring up a screen and this is not working, and I had to reboot my computer and it was off. Right? And it came down to one table scan on one table that went over a threshold. So it was okay below a certain threshold because it fit in the limited amount of memory we had in those days. But as soon as it went over that and it started to swap on disk or whatever it was doing, all of a sudden it was 100 times slower. And it just choked everything because that table was accessed by every single user doing almost any operation. And so it was one missing index and one bad query. Right? And again, it took us 2 days to find it, but it took 2 minutes to fix it, and it was done. And it wasn't even a very big table in that case. So it really happens. Anyway, so the point is, got my knees skinned enough times to know that this is a very, very common problem. So the next enemy is somewhat related, but it's basically concurrency content. So if you have a database, you're going to have things being shared, right? And there's 2 ways today that this typically happens. One is if you have a transactional database and user 1 wants to access something and is holding on to it too long because maybe I've never seen this happen, I'm just kidding, this happens a lot. The developer kept the transaction open or left it too big of a transaction window. Very, very common problem, right? Start a transaction, write some data, do 55 queries that each take a second, and then close the transaction. That's a bad way to do it. So anyway, if that user is holding it, then essentially what happens is every other user is going to wait until that resource is freed if they need the same thing. So that's one way it happens. But there's another way today, which is that with some of these newer in-memory databases, a lot of them are for good reasons, right? But they're architected as a single-threaded system. That the database engine itself is single-threaded. And there, basically, if you have one thing that takes too long, even 5 seconds in a system like that, you can slow the whole thing down. You can just bring it to its knees and make it a screeching halt. Why? Because every request is served in order, and it can only do one thing at a time. Now, it does make the operations themselves much faster, but if you have one mistake in a system like that, you can totally kill it. So who uses that type of architecture? Redis is one. I'm not sure if they still do, but VaultDB was another. Anyway, so some of these engines are specifically designed that way, but boy, you have to test everything. Everything if you want to keep the attention. So, and the third enemy, which is also very common, is basically slow writes. And so what do we mean by slow writes? It's the problem I told you in the beginning, where you have lots of indexes. That's almost always the cause of slow writes. Or you're doing things where you're updating big batches of records. You never want to do that either in a production system. You know, of course, you want to totally avoid that, right? So, yes?
Have you come across any tools that makes the developer's job easy to write better queries or catches it at the development phase itself?
That's a very good question. The question is, are there any tools that catch this at the development phase? The answer is it's not. There are none that are terrific. You can use the explain facilities and that the database vendors give you. There are GUI tools that will do the same kind of thing. But usually there are tools that more as a DBA or system administrator would have. So, but I'm going to talk about our kind of newer philosophy on things, because I don't think the developer should actually be able to get into this kind of trouble in the first place. This is really what I think is the problem, actually. It's like, how come it's so easy for one programmer to write a query that just brings the whole thing to its knees, and how come the system doesn't actually catch it itself? It should, because the database knows it's doing the table scan, right? I mean, it's not that hard to figure out. I mean, you can even instrument it yourself and find out what to do. So I think it's a very important thing. So that was a very good question. And I was able to answer it. So the main point is that the challenges apply to all types of databases. So we have a lot of new database tools. A lot of these tools are evolving very quick, and they really are, some of them are really terrific. They really are. But if you look behind the covers, you'll see that the same kind of techniques like B-tree indexes, there are better types of indexes, blue filters and things like that that are coming out. But even those are things that were talked about 10, 20, 30 years ago. So most of these techniques have been around for a long, long time. And I have kind of a joke, but there used to be a database called, does anybody know how DB2 got its name? What was the predecessor to DB2? You have to know that. Nobody? It's close. It's actually close. It was called DL1, Data Language 1. What was Data Language 1? Data Language 1 was a hierarchical database structure. Why? Because disks were so slow in those days. This is back to the 1960s, before I was born. Anyway. But this goes back a long, long time. But the point is, the disks were so slow that they had to actually construct the data on the disk in such a way that they could retrieve it quickly enough. So you have to actually, as a developer, actually figure out the hierarchy exactly where the data would go, and they would actually write it to disk loops. It was pretty amazing. But it did actually perform very, very well. But so the reason DB2 came out was because that was hard to do, right? Very hard to do. So DB2, the idea was, oh, let's do things based on set theory. That's what Dr. Cobb was working on at IBM. And so he brought that out, and it was a tremendous advance. But it was much, much slower. Right? Because now you could have a B tree that was structured that way, but the data itself wouldn't be, especially when you're doing joins and all those kinds of things. And it took years and years and years to get that technology better. Well, it's just kind of interesting because if you look at NoSQL databases today, especially the ones that are document-oriented, they look an awful lot like DL1 in the way that they work. And they actually can be more efficient because of that, because you basically are building a structure, but guess what? You as the developer have to understand that structure. So the point is, you can run into all these same problems no matter what engine you're using. You really have to know what you're doing today. And like I said, I hope the tools get better, but it's not such a big deal. So what's the moral of the story is, no matter what database engines you're using, it's not very easy to scale them. So you have to really know what you're doing, and you have to really plan for it. So to give you a little guideline on this, I came up with something I call the laws of databases, which are a little bit a joke, but true enough, right? Which is, small databases are really, really fast. Big ones are really, really slow. So keep them small. That's the easy idea. And the small databases work well. Why? Because there's plenty of balance between CPU memory and disk to actually make it work. And if you look at any scaling technology, if it really works, that's why it works. Because the ratio of CPU memory and disk is not off. Right? You have 50 terabytes on one machine. I don't care how fast the machine is, you're going to start to bog things down. It's just not going to work. So what's the answer then if you have to scale a database? And so you'll hear all kinds of different marketing terms and everything else. Of course, we're a sharding company, so this is a little bit marketing oriented too. But the truth is, database sharding is the only actual effective technique for addressing this. And every product that scales effectively is doing database sharding in one way or another. Now, we didn't invent the term. The term came from, who knows who popularized it. I won't say who invented it, because there's a lot of dispute about that. But who popularized database sharding? Anybody know? Not Mongo. No, not eBay. Close. Another big company.
Amazon.
Nope. Google. That's right. What was the name of the paper? The most famous paper on database scalability is ever. Anybody know what it's called?
Sharding.
It talks about sharding, but it's big. It's before MapReduce. Big table. That's right. That's right. You already got one, didn't you? But who answered the first question? We can have one out. Who said Google? Yeah, good. There you go. Good. So anyway, they popularized it, right? And the term comes from broken glass. So it means that you're taking a big database and you're breaking it up into smaller pieces. Simple concept, right? But we want to really talk about what this means and why is it that every database engine is doing this in one way or another. Even the ones that tell you that sharding is horrible, the truth is they're doing sharding too. I guarantee it, right? Mongo's at least honest. So here's the Wikipedia definition for database sharding, and it's basically horizontal partitioning is a database design principle where rows of a database table are held separately. So So that's what it means, is you have different servers, and you have rows or objects of data on different servers, and so you spread it out that way. And each partition forms part of a shard, which may in turn be located on a separate database server or physical location. So that's what database sharding is, and that's how it works. Even if you look at Hadoop and MapReduce, it's still using sharding, because what do? They take big files and they spread them out across a lot of machines. It's still the same basic idea. So, but the simple definition is take a really big database, break it into smaller databases across many servers, and use a shard key to do it. So use some value to figure out the most logical way to split your data. That's the simple answer of how this works. So if you get down to what any product you're using is doing when you're scaling, it all has to do with that, right? Some sort of key. Sometimes they ask you for the key. Sometimes they have some magic behind the scenes where they're doing it themselves, but they're still using the key to do it, always. So what's the key to database sharding is, if you read any paper on computer science, what's the thing that makes parallel processing effective? What kind of environment do you want? The answer's right there. That's a good
Stateless.
shared nothing. What do I mean by shared nothing? Does anybody know Amdahl's law? No. Anyway, it's fine. Okay, anyway, but the idea is if you have a system, and if you have two components that have to do work, and they're dependent on the same thing, you're making it a contention point. So that's a shared something environment. Or sometimes you'll even see databases that advertise that they're shared everything is a good thing. I don't think that's a very good thing. But any paper on scaling in computer science is, if you have a true shared nothing architecture, then every server can go as fast as it can go. That's what you want. So you want to get shared nothing environment.
Are you saying you don't replicate?
You could replicate, that's fine. What you don't want is, I'll give you an example. There used to be things called transaction managers. And those were centralized points for coordinating every single transaction in order. That's a shared component that will slow down the works. That's a bad thing, right? And people tried to optimize them and make it faster and all kinds of other things, but it didn't really work. So what you want to be able to do, if you're replicating, it's fine. But even the replicas shouldn't be dependent on the master or something like that, right? And each shard or each server, like if we look at this picture, I think you'll see it is in this picture. Basically, let's say we're going to shard something by customer ID. So we have 4 shards across the bottom. We have application servers across the top. We have clients, which are the database driver, let's say. And basically, what you have is for each partition, you're going to have, using a modulus algorithm or some other sort of hashing, you're going to say what customer ID goes in what server. That's a shared everything environment. So, and sometimes you do have to do that, but you don't want to do it much. I think you earned a poster if you get one. The last one, okay. It's kind of a cute thing with the posters. We were talking with our marketing team, and they said, "Wow, you're doing a book. We should do a book signing." I go, "Well, how am I going to sign an ebook?" So this is what we come up with. So anyway, so there's another architecture for database sharding, and some databases do it this way, where they have a proxy server in the middle. And so basically the application servers talk to the proxy, and the proxy server makes the decisions. And sometimes the proxy is even on the database servers themselves. So I've seen it kind of all 3 ways. But fundamentally, it's doing exactly the same thing. It's deciding somehow, based on the data and the shard key, where should I go? Other than that, it doesn't really matter. So the point is, if you understand this, you understand how any big data scalability infrastructure is going to work somehow and fit into this. And we'll talk about the consequences of this and what it means, because that's where the rubber really needs to go. So if you do it right and your cluster is balanced and it really is shared nothing, what should you get? You should get linear scalability. That's the key thing, especially when it comes to writes. Writes are the hardest thing, by the way. Writes is where, when you know your writes can't go any faster, that's when you have to scale. If your reads are not faster, you can sometimes add an index, you can use more memory, you can do lots of tricks sometimes to kind of stave it off. But if your writes are too slow, you have to shard it. You have to do something. So, okay. So why does this all work, database sharding? Again, it's just because we're keeping the databases small. What happens when we keep the databases small? Well, database engines for years have been good at using memory and CPU, always. That's been evolving over a long period of time. The newer ones, especially the in-memory databases, you can't put as much on one server, but they're really good at using memory, right? So that's the real reason, is you're changing the balance of the amount of data and the amount of CPU and memory. And when that balance is right, we can get things going 100 times faster sometimes. I mean, it's amazing the actual difference that you can actually see. My partner Andy is from the UK. And he's got, I can't imitate his accent. I'll totally remember. But anyway, in early 2008, I think, or 2007, when we had just started the project, I said, well, do you think this sharding stuff will really work? And anyway, so he made a test, and he called me up one day from, he still lived in England. He lives in the US now, but he lived in England, and he called me up and he goes, sharding works. Anyway, so it really does. But that's why. That's why. So, anyway, the index trees are smaller, everything gets better, and also management is easier, right? It's easier to back it up, it's easier to move things around, everything is easier, right? We have it on smaller chunks. And when you do it right, you get a CPU graph that looks like the bottom one instead of the top one. So it's mostly user CPU, it's not working too hard, you're not stressing out the memory, you're not stressing out the disk. That's really the kind of picture that you want to see. And this is also, an after picture from a real, yes?
Does solid-state storage reduce the benefit of sharding?
So now the solid state, I'm glad you asked that question. So you're right that I/O is a big deal in databases because that's what it's all about, right? And solid state is getting a lot better. It's getting a lot better. We actually work with solid state technology and are optimizing for Flash. It's fascinating what you can do. But still, what we're seeing is the I/O still is a bottleneck, right? And especially for writes, you can still only write to Flash at a certain speed typically. Now that's getting better too because we have PCIe Flash, which is going to get rid of the bus. There's a lot of things coming out that are going to be much better, so it does help.
And there's a thing that I keep hearing about, and but I don't know if it's really mainstream yet. It's just like UltraDIMM, where you've got like SSDs built into RAM sticks.
Yes.
And it's really like supposed to be ridiculously fast, and it scales with the more you add it, the faster you can.
Well, I actually do some work with the company that makes that product.
Yellow?
SanDisk. Anyway, SanDisk has it now. Yeah. They're in partners with that other company. So anyway, so it's interesting. So I'll kind of tell you what I think the 3 levels of Flash are and what they really can do. But before I answer that, your first question was, does it mean you don't have to shard? What it does mean is you can do more on a single server. But still, if you have big, complicated B trees and things like that, you're still going to run into barriers. Now, I haven't tested it yet because the stuff is so new, we can't really get it, a lot of it easy. But the truth is, maybe instead of you need a half a terabyte shard, maybe a shard can go to 2 terabytes or 4 terabytes or something like that. I have actually, though, an actual use case now where a customer has PCIe Flash, 3 terabyte database, something like that, and it's still not very fast because it's too big. So with a regular relational database, I think we're still doing this. Now, on the flip side, people are also working on the software side to make it work with Flash better, and that'll help too. But here's what I think. One of my architects pointed this out. I said, what are we going to do? Because I said, UltraDIMM is going to be so fast, maybe nobody needs to do any of this anymore. And he said, no. He said, the data is going to grow so much, this is not going to matter. And I do think that's what happens. By the time any of these things are mainstream, we're going to have 10 times or 50 times more data anyway, so it's going to be a problem. Right? And then we have to get the price down and everything else. So anyway, so with Flash, there's regular SSD drives, right, which are very fast. But what happens is they use SAS or SATA, like a special regular communication bus, so they can only go as fast as that. And that can get overloaded. PCIe is closer to the host bus, and so it goes faster. So that's the next step up. The UltraDIMM or something like that is very, very promising. But what I've heard is that there are certain characteristics it's very, very good for, other things not so much. So I think for some, and it's going to be, I think, initially very expensive. So it takes special servers with special BIOS, So it's not going to be mainstream for a while, unfortunately. I know, but the first day I read about it, I went, wow, this could be really fabulous. But there's all kinds of stuff going on with persistent storage to make it faster. There's all kinds of new efforts. And so in the next 5 years, things will change for sure. But PCIe is very real. And PCIe will be available a lot. But like I said, even with a 3 terabyte database, I've seen it quite already. So, wow, that was exciting. All right. Yes?
Does the distribution of your data depend on how well you select your shard key? What if you select the wrong one?
That's a very good question. I wish I had more posters, but if you send me an email, I'll take one. So because that's the whole point of the next part of the talk. Is how important is it to pick the right shard key? What happens if you pick the wrong one? And it could be a total disaster if you pick the wrong one. So I'm going to talk about that pretty quick here. So before I do, there's a pet peeve I have, which is that all data is relational. So I don't care if you're using a NoSQL database. Data doesn't mean anything if it's not related to other data. And what do I mean by that? There's a group of us here, right? We're all individuals over at one meetup. Okay, so that's a one-to-many relationship. So I believe it's a relational world. I was just educated that way. But it is true that I have noticed this, is if you understand your data relationships and how your data works together, you're going to do a lot better in structuring your database and your infrastructure and your architecture. So I'm not going to do a big thing on this, but data modeling is key. And data modeling with a NoSQL database is probably more important than it is with a relational database, because there's no rules. And if you do it wrong, you get into a lot of trouble. So the point is, the relationships are there, right? We're even there in your code if you're doing things in memory with data. They're always there, right? You have lists and all kinds of related things, right? But in a relational database, you get some help, not a tremendous amount, but some. In a NoSQL database, you don't get any at all. So let's get into the sharding and shard keys. So there's two kinds of sharding in the world. One is called black box, and one is called relational. The relational, we coined that term, but it's a pretty commonly used, I think, now. So what is black box? Black box is automatic. It's really nice because in theory, you don't have to pay attention to it. So it works great for NoSQL databases. Why? Because the NoSQL database doesn't know anything about your data except for what the key is anyway, and the value is totally applying to it, so it doesn't have any idea. So it's very easy for a black box sharding to automatically distribute data using some algorithm in a very fast way. Cassandra is probably the best example of a black box sharding product. It does phenomenal ability to distribute writes. You can write huge amounts. Relational sharding, on the other point, is where you're actually grouping data together so that you have similar data in the same place. Why? Because we want the same data to be on the same server. So I'm going to skip ahead a little bit because I don't want it to get too late. But
what is the example for the relational sharding? Maybe which one uses this?
dbShards does. No, but other people do too. Anytime that the database system is allowing you to pick the shard key and decide the sharding strategy, it's relational sharding. So Mongo is kind of in the middle, sort of, right? Does it that way. You can pick the shard key and ranges and how they work. So it really is pretty cool to do it that way. But so sharding for NoSQL is a piece of cake because why? It's just put and get by key. So it's really easy to do. That's easy to understand. Relational sharding takes a little bit more because now you have different kinds of data and you have to make sure that they're sharded together. So what do we mean by that? The yellow table here is the shard parent, the primary shard table. So it's the customer. We want to shard by customer in our example. And then we have order and order item, which are children of that table. We want to make sure that the customer's orders are with the customer. Why? So that we can read all the orders for that customer from one place and don't have to go to a lot of other places. That's the real drawback if you're doing a NoSQL database and you have this kind of structure in your application, because now you have to nest those things in documents or make separate document sets, and then you have to shard them different ways, and it can be pretty horrendous. To answer your question, you shard it the wrong way. And then the blue tables in our example are global, because usually there's some small tables you can just put everywhere, so you don't have to worry about those. So in a relational sharding, show you what code looks like. But basically, if you're looking at SQL kind of code, but there are other tools and languages that do it too, some JSON-based. But basically, we're looking at the key actually and parsing out things and figuring out where to go. So everything in blue here is telling the engine how to shard. So that's how you do that. So, but what's the key advantage here? So, just going to skip to. Okay, so what's the key point here? The key point is what I call the database sharding end game. What's the real goal? Is basically what we want to do and make sure happens is that there are different kinds of actions you can do in a distributed database. And by the way, a distributed database is great because why? It's distributed, right? It's also horrible because it's distributed. What do I mean by that? Because when it's distributed, you can, if you're doing things right, you can do the share nothing game, and you can have things go really, really fast. If you start to do a lot of distributed operations across lots of servers in that cluster, it's going to be worse than it is on a single database. So you really have to be careful and understand how this works. But so there's 4 basic operations that we've identified that happen in this distributed system. Shard read, which is reading from one shard. Shard write, which is writing from one shard. Multi-shard read, which we call go fish, means you don't know where to go, so you go everywhere. So you're scanning lots of things. And multi-shard write, which is where you're doing a distributed transaction across 2 or more shards. Right? So these are in the order of performance. And the first 2 are great because they're shared nothing. The last 2 are horrible because they're shared everything. Now sometimes the third one is okay because sometimes you can do almost like a map reduce on the fly, and that can be very, very beneficial to an application if you don't overuse it. If you do it too much, it can be just as much trouble. So what is the end game really? The end game is really simple. Is what we want to do is we want to have as many single shard operations as we can. It's really simple. So how many of you have to bring back lists of records? Like orders for our customers, something like that. Anybody have to do that in your applications? Okay. So if you're using black box sharding and you don't control that, chances are that stuff is going to be spread all over the place. And that's going to make a lot more multi-server interaction. We talked about the fact that I/O is getting better and better all the time because of Flash and PCIe and all these different new innovations. Well, so that's even getting to be less of a barrier. But what's really the big barrier between these machines? The network. And I don't know when that will get better, but I can tell you that 10G is becoming pretty prevalent. And we know that even with 10G, even though it's very, very fast, the network calls themselves are very expensive. You can't make too many of them, even though it can do a lot. So if you're sending big files, it's really, really fast. If you're doing lots of little things, it's not so good. It really falls apart quickly. So the point is that you really want to keep things so that you're doing single shard reads and writes. And if you have to read lists a lot in your application, it can be real trouble when you have something like a NoSQL database, because now what you have to do, you have to embed those lists inside the other objects. If they get too big, you're reading the object, adding to the list, and writing the whole object down. That's not a very good way to do it. Now you can add other indexes sometimes, and it's pretty funky though, right? But that's why I say that structure is very much like DL1 was in the original mainframes. It's very similar, because you had to do things exactly that same way. You had to figure out exactly how much space you wanted and how you were going to allocate things. That's kind of why relational databases got popular in the first place. So, all right, so have we really been looking at databases the wrong way? Like I said, I really think we can do better as an industry, and we're kind of working hard on this, but I'm going to just give you this is sort of my philosophy in life right now. But basically, how do we look at databases? Well, we typically start off with a schema, and you make the schema as good as you can for your application. You probably do a pretty good job at the beginning, right? And you start writing some data, and then you start reading some data, and it all works fine. Typically, that's a good skill set, and everything works fine, right? Then what happens is the application evolves, and it gets a little more complicated. And now what you end up having to do is you have to have different kinds of data, or look at the data different ways or whatever. So now you get into reading the data, doing a little bit more complicated processing in the application, and writing the data back, maybe to the same place, maybe to a different place. It'll be different, right? So it gets a little more complicated. And then when it gets even more complicated, what we have is we have a graph that looks kind of like this, where basically the application is just going kind of frenetically back and forth to the database. And the database is being used really as a kind of a static sort of repository that doesn't really change much. And you're trying to keep with, you're of course trying to keep with the schema that you had because that's what you started with, right? And it gets more and more difficult to make it work. Have you ever noticed this over time with an application that you run into more problems as the requirements get more complicated? Because the original structure we had maybe wasn't really right. That's the truth. And so what happens, yes?
It was probably right, but it was only right given like a small data set.
That's right. It was right given a small data set or a small number of requirements. Right? And so what do we know? It's only going to get more complicated and it's only going to get bigger. Those two things are going to happen. So now what happens is a lot of times you have to try and get data out now. So the data went in kind of the original way you had it. You have a lot of it now. And now you've got to try and get the data out because somebody needs to see a new report or a new view for the business or whatever, and you can't move. So you start to write complicated queries. So I don't know if any of you guys have ever seen this, but I've seen queries that are pages long. I don't recommend that, right? But I mean, don't do programming in queries, right? If you're having to do that, it's really because your data isn't the right way. That's the key thing. And so then what happens is, now you get even more complicated requirements, and you decide that you need another database. So maybe you need a data warehouse, and maybe you need a memory database, or maybe you need something like a text search index or whatever. Now your application is having to manage all the things it had before, but now it's also having to read and write to these new databases also. Okay, so now it's getting really complicated. So now you've got an application that's trying to manage consistency in data across engines that probably don't even have consistency guarantees in a lot of cases. It can get really, really messy. So it gets really, really a problem, right? And so, in summary, I kind of look at it this way. It's sort of a joke, but it's like we look at databases as like a graveyard for dead data. It's not in the book yet, but basically, it's really true, right? I mean, it's you end up with now. How many of you have worked on the system long enough, or had several people work on it, right? And you've seen it change over years, and you've seen the same thing done 3 different ways in the database, the same thing, because somebody didn't understand what somebody before them did. Anybody ever seen that? That can get very complicated, right? So now you have really dead stuff, right? Because you have things that aren't even used anymore. Nobody even knows what's in there, right? So I remember I had a project once where we had to integrate with a mainframe system, and we just needed a simple report out of the mainframe application. And it was taking the developer like 3 weeks to get this report, and I'm like, what's going on here? And it was killing us because we couldn't deliver. So I went to the manager and I said, can we do anything about this? And this application was 20 years old, by the way. And so she looked into it, and it turned out that she actually was the original developer of the application before she was the manager, 20 years before. And she went and looked at it, and I guess about 10 people had worked on it in that 20-year period, and she was involved in what had actually happened. And these mainframe developers had kept adding new COBOL code and new vSAMP files or whatever they were doing to keep making these new structures, and it was impossible to figure out what was going on. So she pretty much took 2 weeks off and worked with the current developer, and they fixed it all and kind of rewrote the big parts of it throughout this 75% of the system. But one of the things that happens is, question?
Yes, but I was going to say, a lot of the complexity you're talking about is, do you think a lot of that's due to people using, I know most places I've seen that, it's because they're using the database as like the central clearinghouse for their service architecture?
Exactly.
And it is, okay.
Exactly. They're using it the wrong way, or it doesn't really fit what they need. Both of those cases, it's exactly true. But there's a bigger problem, right? So I'm going to just tell you kind of a story in the life of a game application. We had a lot of game applications we worked with. They were really hot, a few years ago, and they're very exciting and they grow very, very fast. So let's say we have a game application. We start out, and so it's a multiplayer application, and more than one player can compete in the same instance of a game. So we have a player, a game, and a player game table. Fine, you can put that structure together, no problem. So the game starts to do pretty well. People like this game. Who knows what it's about? It's certainly not Angry Sharks. But people like it. So what happens is, this is kind of how this all comes about, I think. Is what happens is, so now How many of you have been asked that question ever? Like every day, right? That's something, right? And you make the application do something else. They go, you know, it's growing really fast now, and the players are saying that they can't see a list of the games they played. They want to know the list of the games they played. And it's starting to slow down because, you know, now we started out with a few thousand players, now we have a few million. And a few million like every day. And I have, by the way, seen an application go from nothing to 7 million players a day in 90 days. So it can happen like faster than you can go. So you go, okay, well, I got to do something about it. So fine, I'm going to shard it. So great, so that's going to solve this problem. If I shard it, because I need the list of games for a player, I'm going to shard it by player. And that's almost how every game starts, is they shard the data by player, so that the list of games the player played are in the same shard, so they get that list right away. Then we have a nice single shard page just like we want, right? Perfect, right? Beautiful story, right? So now things are cooking, and it's better, and the performance is over, and anyway, we lost a few late nights, but we're okay. So now, the manager comes back, and they say, wow, the game is really big now. You know, now we have millions and millions of players each day, and guess what? The players now, they want to see, if they're looking at a game, they want to see who else played that game. So now, not just the games they played, they want to see who else played it. Well, now the data is spread all over by player, isn't it? So how are we going to do that? We can't, right? Because if we do it, what we have to do is we have to read every single shard to find the other 3 players that played the game we're going to do. That's not going to work, right? So what do we do? So the developer says, well, you know, sharding worked pretty well. So what I'll do is I'll take just the data that I need to do that. I don't need much to figure out that list of games by player. So I'm going to make another set of data, and I'm going to shard it the other way. I'm going to shard it by game now. So now my application is writing to the data by player. It's writing to the data by game to make all this work. So we lived through that, and that seems, hey, it's pretty cool. It's working. It's not bad. And believe me, we've gone through exactly these steps with customers. So these exact things have happened. And I've seen it with Mondo, and I've seen it with just about everything. So, all right, so now the manager comes back again. Right? So now the manager comes back again and he goes, wow, the game is really big now, but we're not making any money. Maybe you've heard of some companies like this. So anyway, well, why does a game make money? A game makes money because there are things in the game you have to pay for to get really good at the game, right? So if you don't know exactly what the players are doing, you can't attract them and make it appealing for them to pay for things. So they go, wow, what we really need now is we need to track every action that every player is doing in the game. Believe me, metrics, but on every click, everything, right? How long does it take them to get to a new level? How long do they play this feature? Because if they can figure out which ones they're hanging around in and which ones they like, they go, how can we make it more attractive to pay them? That's the whole, this is how game companies make money. And every one of them does this. So now they go, oh my God, so now I have, let's just say I have 10 million users a day. I don't know if I can do the math on this, but 10 million users a day. Each user is playing an average of 2 games. That's 20 million gameplays a day. Each gameplay has, let's say, 100 actions. Okay? So that's a lot, right? A couple billion, I think? Something like that, right? So now all of a sudden you're talking about 2 billion somethings a day. What are we going to do with that? Well, okay, we'll get a data warehouse. We'll put it in a data warehouse. So now the application has to write to the one shard by player, the other shard by game, and now it's going to pump data to the data warehouse also. Pretty exciting. But it's the only way to do it. And then they can run reports on the data warehouse and a few weeks later get an answer. But at least they're going to get one. So that's all fine. We lived through that. Now what happens is, now the manager comes back again. He says, you know, the players want to know, now it's going better. We're starting to make some money. But to make even more money, we want players competing harder. So how do we make them compete harder? We want a leaderboard. We need to know who the top 100 players are all the time. Well, take this problem, right? You know, it's not a very easy problem to solve if you have, you know, that many gameplays a day and you have to constantly figure out who are the top 100. You've got to take a different infrastructure. So it probably takes an in-memory engine, right? Redis is a very good solution for this kind of thing. A lot of people use that, so that's fine. So you make that, you get the top 100 players, and that's off to an alarm, right? And now, guess what? The manager comes back again. This is the last one. At least now we're ready to quit. The manager comes back again, and the manager says, now the players want a leaderboard for everybody, all 10 million. Because anybody wants to see where they are and how they rank in the whole scheme. And not only that, they want to make teams, and they want to have teams that are by community or whatever. And anyway, so now it's like really complicated. So how do we look at that in our field, right? Well, this is a fantastic challenge, right? So we take a few weeks and we design a solution. We go, plus they're probably going to ask for other things. We go, we're going to design a leaderboard that's so fast that can scale to anything. We can make all these categories and we can just accomplish anything. And let's say we're going to use Redis or some other low-level tool to do it, fine. That's what we're going to use as our approach, but we do it. We spend the time to design it right, we build it, anyway. Let's put it this way. It's not going to be the simplest thing, but we make it work, right? Matter of fact, it's so successful, right, that we get offered a better job. So we get offered a better job, and some new poor guy comes in, person, and has to actually figure this out, and they say add something to the leaderboard, and anyway, he can't do it. So what does he do? Make a whole new leaderboard. This is exactly how it happens, and it happens a lot. Why? Because they never told you had the time to write the whole book on how you built that engine to do all this, right? And you probably built it honestly, you probably built your own database to do it. So that's how you end up with this kind of picture at the end. Yes?
From a business perspective, how often do you have to wear the hat of saying, okay, well, he's probably going to want this community aspect for the top 100. So is that just presenting options to the monetization person or whoever's asking you for all these features? Or how do you best go about saying, look, you're probably going to want me to spend an extra 2 weeks on this?
That's right. That's right. And if you're honest, you do that. Right? That's going to make a lot more work. But usually, what I've seen is people are in such a hurry, and there's so much business pressure on these type of games, especially, that they don't have the time to do much extra. Right? And so it happens. And so it's very common for something to get built as a feature and another feature and another feature to get completely refactored and built again. Look at Facebook. Look at all these big companies. They have done it lots.
Is that just so much less efficient than saying let's just spend 2 months and knock this out?
Yes, it's totally less efficient. You're saying exactly the right thing, but it's not how I've seen it work too much, right? Because people don't have enough time. If you also did it that way and you were going to build something like this, you would also take the time to document it so somebody else could come in and actually support it, right? So that would also be better. Right? But the point is, yes.
That's not restricted to the game. In many cases, if you ask a management, would you want this feature, which an architect might do is obvious, the answer will be, of course not. And the next panel in the cartoon is, why didn't you put it in?
That's right.
So frequently what you end up doing is, this is going to, you can see where this is going, and you put covertly, namely not hiding it, not announcing it, you put the capabilities into what you're doing. And then the next week when they come in later and say, can you do this? We'll look at it. Turn on that if statement. The problem is there's a horizon problem. That's who wants to be done on what time frame and what the implications are.
Yeah, when you take the extra 2 weeks to make your game, your company's gone out of business if a game company.
From a business perspective.
My point is this: more often, if I walk into a site and say, you need to put in a trace facility so you can understand what goes wrong, the answer is, of course, nothing will go wrong. It then gets put in piecemeal over the next 2 years, which takes you much longer than it would have taken to put it in the boilerplate to begin with.
So you put in a dummy one instead.
Right.
So it is the right thing to do. But I can tell you can go overboard too. I had a developer who was so conscientious, he suggested so many features of the application, he extended the project by a year. So you can go the other way too. But if you do see sensible things, you should try to take care of it.
It's just a matter of presenting those options to the who has the money or who is kind of making the decisions for the whole pipeline.
And if you work for a nice, sensible place, it's a very good strategy. Anyway, so the point is, this is what I think is wrong, actually. And I should have seen this a long time ago, right? But I've used object relational managers. I've used all kinds of different techniques to try and make this easier between the application and the database. But this idea of using the database as kind of a static repository and having the application do all this interaction back and forth and all this stuff is really a hard way to go. And I think there is a better answer, and I'll show you kind of a little bit about what our idea is. So, and this will explain what the t-shirts were about also. But basically what we're after is it possible to have an agile view for big data? Can we really make a big data infrastructure into an agile environment? And we do think there's a way to do it, and it's based on a very simple concept. And I'm embarrassed to say that I should have seen this sooner, because I wrote a book called Software Pipelines, which is all about flows in software and treating transactions as flows. And the idea was right there all along, which is, can you look at data in a streaming way instead of a static repository? And can you do a lot more with it much, much easier? And the idea here is, there are two symbols here. One is a stream and one is a view. And the idea is, can you take data as a stream? Can you manipulate it into what you need for a given requirement? Put it into a view which is persistent and queryable. And then take a feed from that and do something else to it when you need to, and then do it again and again and again. And actually have it be to where there's like no penalty for doing this, except for disk space. It does make more disk space, but the idea would be that you can manipulate the data into exactly what you want. And it's kind of interesting how this came about. A long, long time ago, I was trying to cram an application into a relational database. And this customer had it was like a bidding system for a hospital supply company. And it was very complicated rules, and they had to do all these complicated queries. And queries were taking, I don't know, 20 minutes to an hour each. But they wanted to run 200 of these queries a day, otherwise they couldn't bid these contracts effectively. So anyway, we tried and optimized and indexed into different structures and we couldn't get it to work. So finally I had a good C programmer on staff, and I went to him and I said, what do you think would happen if you just dumped this data into a flat file on disk and just scanned it and just rolled it up? Anyway, he tried that, and it was no lie 100 times faster. 100 times we were able to do it. He was able to do queries in seconds that were taking hours. It was amazing. So if I was really smart, I would have called that MapReduce and made a fortune. But didn't. But it was that exact same approach. And it used a lot of memory, and it used the disk buffers and other things that were all sitting right there all the time that a relational database can't take advantage of. It's fascinating. Really, really fascinating, right? So, and it would have been very easy to parallelize and all kinds of other things, but we didn't even have to do that. So I learned that if you get the data in exactly the form you need it for the application, things are like that fast, sometimes 100 times faster, with actually very little work. And so we looked at this, and it's very easy to actually structure things because you can think of it one step at a time. And if you have to add all these requirements, you can add them one step at a time. And it's easy for somebody else to come in after and go, oh, this one is doing this, and this one is doing this, and this one is doing this. And that's how they work. And then you can access the data in a sensible way. And so, sort of our dream is, wouldn't it be nice if you could work with data as a continuous agile stream where you could support agile views of the data as needed without kind of having to worry about this. You could just do it whenever you want, right, and maintain data integrity. You could do it across database engines when you need to, when you need more than one. And most importantly, you could keep the application pretty simple because the application only needs to understand that very first schema or something like it to be able to do all this, right? And basically get back to simple reads and writes, just like we started off with. And so that's kind of where we're headed at. So the t-shirts you guys have is about a new product that you guys are the first people to see the name publicly, by the way. We're going to be announcing it at Cloud Expo next month. If anybody wants a free pass to Cloud Expo, you can email us and we'll get you that. The first 25 people that email us will give you, like I said, a poster and a free copy of the book as well when it comes out. But anyway, you'll hear a lot more about this. I can't go go into too much detail now because we have not announced this product. So don't go putting this on the internet yet. I can ask you to do that, but anyway, but this agile approach is really paying dividends. I can tell you, we've gone through maybe a dozen use cases so far with customers, and it's amazing how quickly we can actually solve these problems and how easy it is to look at it afterwards and go, oh, that's what it's going to be. So, like I said, I think it took me longer than I would have expected in our team, but we really do think we came up with something that makes things a lot nicer. All right? Yes?
Is it possible to optimize the system without using more than one database?
The question is, it can be, right? But it depends if what you need can be done with that database, right? So that's the real question. So there are a lot of requirements that can be done just fine with Oracle, right? Use it correctly. But what typically happens, right? And I've known this for a long time in software, is if you use the right tool for the job, you work 10 times as hard and you get a much worse result. Right? It's much easier to find a tool that really does what you want. You know, it's MapDB is actually structured this way. If you guys want to check out anybody here Java developers? Okay, so MapDB might be kind of interesting. But it's actually structured on this kind of basis, is that it's dynamic and it can have lots of different structures and different even internal structures very, very easily with the same basic API in the front. Kind of very clever how developers do it. And that's kind of where we got a lot of these ideas from. Okay, so questions now, I think.
Oh, before we go on to Q&A, I just want to give a great big thank you to Cory Isaacson, CTO. Question. By the way, there's plenty of beer, sodas, junk food left. Feel free to grab it at any point, by the way. First question? Right there.
So I've seen a couple presentations back to SOAR. Remember? To SOAR.
No.
So they put a middleware piece between the SQL statements and they shard it out and they can use Amazon Web Services and that. So I'm just kind of curious what you thought of that. I fundamentally like your approach better, but they're having success. And so what they're doing is they're just, they're automating. You don't have to change your statements, you don't change anything, you don't do it all underneath.
Yeah, I mean, that's basically what we've been doing with dbShards for a long time. But the truth is that when you get into actually optimizing the things I all talk about really trying to optimize for the database sharding endgame and making it mostly single shard reads and writes, you have to do work. I've never seen it where you don't have to do something with the application. And believe me, there's a lot of people that have attempted to do this, and it's still not quite right. But let me know that kind of name, and I'll check it out. Maybe they're doing something different.
Next question. Anybody? Okay, thank you all for coming. Enjoy the beer.
Thank you very much.